Hey kids, here we are for what is the last video for a little while. So again, thank you for your patience. This is also the last lesson of the units, chapter 14. We are done after this. And this warm-up isn't really a warm-up. It's number 29 from your homework, as you can see. But I just wanted to make sure because in the video I did a rectangle. Um, and showed you how to do those boundaries. And then I know I showed you the circle too and how to do that, but I just wanted to highlight that with the triangle you were writing equations of lines, which was an algebra 1 topic, right? So the boundary, right, of the straight line obviously is when x is always 0, and then but the green side with the given the points that I have was when y was going to be in terms of x, 2 minus x. And then the blue side was when y was also in terms of x, but was x minus 2. And then, of course, you do your derivatives and restrict. Make sure you know where your x's and y's have to stay between. So you have your endpoints to check as well, right? So took my derivative, took my derivative, took my derivative. And I trust you can do the rest of this. And the answers that I got 0, plus and minus 2. Comma 4 were my absolute maxes, and 1, 0, -1 was my absolute min. So remember that this is what we did. We started 14.7 day 1, finding local extrema on the inside of a boundary we created on a surface. And then the last video, what we did was say, okay, now we're going to include the boundary and we want to find the absolute, right? So that's what we did yesterday. That's what this warm-up is about. Today we're going to add another component. We're going to add a constraint on where those x's and y's can be. So not just on the inside, but we're going to say we're going to restrict ourselves to just the boundary. So this is called Lagrange multipliers. Lagrange is a mathematician, an Italian who then became a French citizen. I don't know if math was easier to study in France. I don't know. But anyway, he's Giuseppe or Joseph as we call him. Lagrangia in Italian, or just Lagrange by us. But I want you to notice this surface here. Can you see the kind of level curves drawn on it, right? If you're looking down the z-axis of that, can you imagine all the level curves? There's only 2 there, but then this red, do you see this red curve here? That's what we're going to say is our constraint system. So we don't just want the max and mins on this boundary or inside. We're going to ignore the inside altogether. I'm going to say we want the maximums and minimums of f only if they're also on this, what we're going to call restriction or constraint. And Lagrange found a way to do that. He's just so, because there was no TikTok. Right, so here we go. So again, last section we found the absolute max and mins on a region that was within and on a boundary. So some kids will ask me after we go through Lagrange, well, can I just do what I did before? You can sometimes the math is nastier, which is why Lagrange came up with this shortcut. And also University of Maryland is going to specifically say for problems, use Lagrange multipliers too. All right, so we gotta learn it. All right, so again, what we're going to do now is we only want to know about extrema on the boundary. This is an optimization problem. This is like volume, right? When we were in single variable, if we wanted to maximize volume when we were doing optimization problems, we had to get a volume equation in terms of only one variable before we could do our calculus. Well, now we don't have to. So we might want to maximize the volume of a box, but one side of the box has to be this size, or something like that. Or maybe I want to minimize another Calc 1 example was minimize the surface area of a cylinder, like a Coke can. But we always had to replace variables so that we were taking the derivative in single variable. We don't have to do that now. I'm not going to do any word problems. I'm just going to get the process down. So just abstract formulas, abstract constraint system. Not going to give you an application yet. But that's what we are doing. We're doing max-min optimization problems, just in more than one variable. So remember in Calc 1, what we looked for optimization was momentary flat parts, right, and endpoints, right? So that's where the derivative was equal to 0. We're not going to deal with derivative does not exist because I'm not going to have a broken surface. It's going to be closed and continuous. Well, in Calc 3, notice this is mine. So the green function is my constraint function, but remember, I'm not interested anymore on any of the domain values from inside the circle and where they end up on the circle. I'm only interested in the domain values on this green surface in the domain and where they end up on the surface. So this red curve is the intersection of G and F, but further, I want those of all those intersection points, I only want the ones that make F either maximize or minimized. So the green function we call G, it's equal to a constant. And then of course we have our surface function, which is Z, our height, right? So since there's too many boundaries, we cannot test all of these values to see who's the highest and who's the lowest, which is what we did here. If we wanted just the endpoints, we would say, right, I'll just plug in the values of the endpoints. Lagrange, good old Giuseppe, why do I say Giuseppe? Giuseppe, he came up with a shortcut, and what he thought to himself was self. When the max-min points that we want have to be on the green boundary, where g of x is equal to k, not inside, and further, of all those points up here on G, we also must be the highest and lowest of F. What he thought was, if I look at the level curves, so I'm looking down at that purple surface of all the level curves, where the max-min values are going to occur is where the level curves of the surface are tangent to the level curves of the constraint. All looking down on 2D. Well, that's kind of difficult to think about. So imagine that I found a point. Do you see how this is kind of a momentary stationary point here on the red curve, right? I also have one here. I probably have one here. So, but let's just look at this one. It has an image down here, right? Maybe it's here, maybe it's here, right? I'm going to put it here just because to make my drawing easier. So there's its image on the constraint. Now, I know up in space there's a tangent line that I could draw to the curve there as it exists on the surface, but that has a shadow down on the constraint, right? And now remember, if we're doing level curves, that when I'm looking down, those two tangent lines are the same, aren't they? They look, right, if you compress them down, if you lower the height, they're going to lay on top of one another. Okay, so the tangent lines are shared. Now let me ask you about the normal to the curve. The normal to the curve, right? Thinking. The normal line to the curve there has a direction, doesn't it? What's the normal line's direction called? Oh, isn't that grad f? Isn't that a vector of the partials, right? Didn't we do that before? So there's the normal line to the curve. Do you agree that there is also a normal line to the tangent line down here in 2D? Yes? However, you can't guarantee that they're the same size, but they're parallel. So in other words, grad f is parallel to grad g, which means that their relationship differs by a multiplier. Ah, Giuseppe, that's where you came up with your multiplier. And he decided he was going to call his multiplier lambda. So there's his grand idea. Yay! Right? We approve, we approve. This is going to help us, right? This is going to be a shortcut to testing all the boundary levels that we, the boundaries that we could maybe find and test which one gives us the highest. We're going to basically narrow our search. We're going to use his system of equations, which is what this is going to turn out to be, to narrow our search. So, oh, there's another picture. I put this on your handout in the top right corner. This is not the same surface that I just showed you. It's some other, but it's a picture of a level curve of some 3D surface, right? So I'm looking, my surface has height, steepness, and whatnot. And those are the level curves. And then there's my constraint winding through it. Well, you can see the constraint hits the surface there. But what he proved is that where they share a tangent, the level curves of the surface and the constraint, where they share a tangent, that's going to be the maximum, not overall, but the maximum that is the highest value of f, given that that point has to lie on the constraint. The domain x and y have to satisfy the constraint. Okay, pretty cool. Pretty cool, that Joseph. All right, so let's just dive in. So I have a plane, and notice that in the domain, the green function, I've got a circle of radius 1. I don't really care about that 1 when I'm doing grad f, right? Because the derivative of a constant is going to go away. So I'm just going to call my constraint to make my grads x squared plus y squared, to make my grad g, right? So there's again my height function, my z. There's my domain. It's a circle, and I know that I also my circle has to be a radius 1. I will use that 1, but not when I'm doing my vectors. So that's what the circle, all the points from this circle, when I put them into this surface, that's where they lie. So there's an infinite amount of points. Can you see which one's the top and which one's the bottom? I can kind of see it. Well, let's go find it. So what does he say to do? Make grad f, which is a vector of partial f's. Make grad g, which is a vector of partial g's. Multiply grad g by lambda, which then looks like this. Now match it up. That's what I mean by expand, like match the x parts and the y parts. And of course z parts if you... It's later, don't worry about that now. Make yourself a system of equations where you have 3 unknowns, x, y, and lambda, and solve for those unknowns. 3 equations, 3 unknowns. Do whatever you can do. Whatever algebra. That's why you take prerequisite classes, right? Whatever you can do to solve that system. The solutions to the system will be candidates for the absolute extrema. They will all be on the boundary curve, but at the same time, they will be points on the boundary curve on the surface that make this, that are the highest of those points or the lowest of those points. So here we go. There's g of x, right, without the 1, because when I'm making my grad g, I don't care about it. So there's grad f, there's grad g. Solve the system. So for the first couple of equations, I kind of write it out this way, but then I kind of just skip to the equations already broken up. So again, there it is. There's me writing it kind of combined. And now I split it up, right? The x is with the x's, the y's with the y's. And now do whatever I can do. I'm going to do a substitution. In this case, I'm going to solve for x and solve for y. And then since my constraint system equation only has x's and y's in it, I'm just going to solve for lambda, resubstitute, okay? So there I solved for x in terms of lambda. I solved for y in terms of lambda, plugged into my equation, and got a value for lambda. Plus or minus root 5 over 2. Don't forget your plus or minus. Now I'm going to take these values and plug back into x and y. and I got x was plus or minus 2 root 5, y was plus or minus 1 root 5, but I'm not done, right? I'm not done. I found the domain values that are on the circle, and by Lagrange, he did, this isn't just him thinking, right? He did prove it. He proved that those domain values will lie on the surface, also on the curve, and further be the most or the least I can get under those circumstances out of my surface. So you have to plug them back into your surface. And since I only had 2 candidates, one of them is positive, one of them is negative, I see my absolute max and my absolute min. Good? All right, let's do another one. Oh, there those points are. Like, couldn't tell. I think you knew where they were, right? All right, so this time I have this hyperbolic paraboloid looking thing, right, with the saddle there in the middle. I, again, have the same constraint, the circle with radius 1. So here, right here, is what that boundary circle looks like when you put all of those points into here, multiply them together and add 1 and plot them on the surface. So of that infinite surface, I have just these, but now I think I can see the heights and I think I can see the, right, the lowest points. But let's have Giuseppe find them. So I took the grad of f and I got yx. Again, the grad g is just 2x, 2y. I'm going to solve this system, but I think I'll probably just write it like that first. And since I already showed you solving for x and solving for y, I'm going to do something a little slightly different this time. I said, okay, y is equal to, right, if x is equal to lambda 2y, well, I just went up to here and I put lambda 2y, and I got that expression, I factored it, and I got 2 possibilities. Right, I got y is equal to 0, or wait, can y be equal to 0? Is that on my constraint? I don't think so. Get rid of it, save myself some work. Lambda is plus or minus root, just 1/2. Now go back and resubstitute into, since you know what lambda is, right? I can go back here and find out my y and my x by substituting in lambda. Right, y is equal to plus or minus lambda times 2x, therefore y is equal to plus or minus x. So I now go to my constraint. What about when y is plus or minus x? What is x? And I got plus or minus 1 over root 2. Not done. I have a bunch of candidates. Plug them in. And I don't like decimals, but that would have, making that 3 over 2 would have made my little blue thing, my little purple sticky too tall. So I used 1.5. So anyway, can you see, again, I have 4 points, but 4 domain points, but I only have 1 maximum height and 1 minimum height, right? Can you tell that that's where they are? And it's not surprising with how nice this shape is, right? Mr. Getz is saying hello. Hello. All right, let's do another one. So this time I have another very simple surface, 5x minus 3y, subject to the constraint. So this time I'm actually going to write out my, like, step 1, step 2, right? Be very algorithmic about this. Find the partials and set up a system with my lambdas. Right, this time I went straight to the system. Right, that is a system I'm trying to solve. In green, I highlighted what my constraint is. This time my radius is a 1. Ooh, ah. So again, step 2 isn't always step 2. It's always do something so that you can solve for your variables. So in this case, I solved for both x and y like I did in example 1. And I got x was 5 over 2 lambda, y is equal to negative 3 over 2 lambda. I put those into my constraint system, right? Squared everything correctly, then did some math. and solve for lambda, right? So no big deal. Then I substituted the lambda into the equations that have the multiplier, and I got negative 10, 6, and 10, negative 6, not done. Substitute in and compare heights. Since I only have two, one of them is going to be the max and one of them is going to be the min, right? So there we go. Minimum at the domain value, negative 10, 6. Maximum at the domain value of 10, negative 6. Minimum value of negative 68. Maximum value of positive 68. Let's do some more. Oh, do you see what I did here? Dagger, dagger, dagger. Three variables. Three variables. Boo. Boo. So I have a system with 4 equations and 4 unknowns. Well, they're still pretty simple, aren't they? So that's my algorithm set up, right? Get my grad F, my grad G, create my lambda, my Lagrange equations, I call them, right? That's the ones with all lambda in them. And then the green one is my constraint. I got X, Y, and Z in terms of lambda. And again, there's plenty of different algebra techniques you could use here. This is just what I did. I plugged into the constraint since I could solve then for lambda, and I got plus or minus 1. And then I went back and I plugged in for lambda. Now I know that should be negative when I put in 1, but I wanted to keep all my positives and all my negatives together. Judge if you will. Judge if you will. But those are my values. Again, not done. Had to plug all of those into, not the green equation, right? Into the Z equation to compare heights. And when I did, I got the absolute max to be 2 and the absolute min to be negative 2 at those 2 points. Good. So domain values of 1/2, 1/2, negative 1/4 gave me my max of 2, and domain values of negative 1/2, negative 1/2, 1/4, which were all satisfy the constraint, also on the surface. But of all the points on the surface that satisfy the constraint as well, those two create the highest and lowest values for Z. All right, one more. So again, this time, boo, I have 3 variables. So again, you can pause the video and see if you get the same things I get. Now, in this one, I'm not super happy about the first equation, right? I haven't had to deal with something. I mean, it's not that big of a deal, but I do notice, right, I'm only in terms of X, and then the second's only in terms of Y, and the third one's only in terms of Z. So this time what I did was I said, okay, well, the second equation, I can solve for, I can make that true, make it equal to 0 when Y is equal to 0 or lambda is equal to what? Right, so I kind of have case 1 and case 2. And then I did the same with the Z equation, right? I collected everything on one side equal to 0 and said that equation would be true if Z was 0, which of course is obvious, right? If you plug into either one of those equations, right? So this time I get when Z is 0 or lambda is 3. So let's take each one of these cases. Now notice first, take the easy case first. In the case when Y is equal to 0, could also be true that Z is equal to 0. Lambda is not involved. Let's just go right here and see what X is when X and Y are 0. Right? So case 1, Y and Z are both equal. Plug them in. X must be equal to plus or minus 1. Let's knock this out. Let's get rid of this, right? Let's just deal with this and put it aside. Substitute into the surface, right? 1, 0, 0 and negative 1, 0, 0, and I get 2 values added up, right? Hold that thought before, and now let's go to case 2. Because if y is 0, z could be 0, which we took care of, or lambda could be 3, right? So let's take care of that case. If y is 0 and lambda is equal to 3, this time I went back to the first equation and said, oh, I need to solve for an x, right? So that I can plug 2 values into the constraint system and solve for 1. So I put 0 and lambda into the first equation up here. Right, I'm sorry, I said 0. No, y, there's no y in there. I put lambda 3 in for lambda, and I got 2x plus 1 is equal to 6x, so x is equal to a fourth. So then I could put x is equal to a fourth in the constraint equation at the same time y is 0. And then I could solve for z. All right, let's get this one out of the way. Plug in to the surface equation. Surface equation is our purple one. When x is a fourth, y is 0, and z is equal to plus or minus root 15 over 4. And I could do this at once because in my constraint equation, I'm sorry, in my surface equation, I just have a z squared, not a z to the first or third or anything. And I got a height of 25 over 8. But I'm not done, right? Because now down here, I had, oh, z could be 0 when y is 0. Check, we already took care of that one. Or lambda is what? Yeah, lambda's 2. So let's check that case. Drop my ring. So I went back to the same equation with only x in it, and because I have a z and I have a lambda, so in that case, right, I put lambda is 2 right there. This time I got x is equal to a half. So I put a half in my constraint equation for x. I put 0 for z and solve for y. Substituted that into the surface. And again, because I only have a y squared in the surface, I can plug in both. Oh, shoot, I didn't type that right, did I? The answer is right, but it's right, the plus or minus root 3 over 2 should be here, and the 0 should be here. Sorry about that. But I get 9/4 when I'm done. So again, these two things should be switched. You can tell I copy and pasted and then just replaced the wrong thing. So, okay, now you have a whole bunch of heights. Who's the lowest? Who's the highest? Right, winner, winner, chicken dinner. And that's it. So try this homework. I'll be back and we'll start reviewing for our test on chapter 14. Believe it or not, you are more than halfway done with multivariable, right? You only have chapter 15 and 16 left. Now 16 is a bit of a bummer. It's the end of multivariable. It's hard. So I did split it into 2 tests that we'll do second quarter, but this is not a year-long course. It's only a semester course. You're more than halfway done. Pretty impressive, my friend. Pretty impressive. All right. I will talk to you soon. See you soon. Bye.